All right, so our video cut off and Zoom crashed. So we're back. Um, and we were talking about logarithmic equations and solving them. I think I gave the example log base 2 of 1/8 equals x. Right, so this is similar to problem number part C on our worksheet. Let's see here. And so we'll do that problem as well. And we already did one similar to part A. So something like this, you might be able to figure out without even rewriting an exponential form. But if it helps, let's rewrite it. And we're going to take the base and make it nice and large. And then switch, we're going to raise 2 to the x power. And it's going to be equal to 1/8. And so if it helps you as well, remember that 1/8 is actually 1 over 2 to the third. And so to get 2 to what power equals 1/8, we're going to need, well, yeah, you can actually even go and rewrite 1 over 2 to the third as 2 to the negative 3. And that really tells you the answer there. X, the exponent that you need to put on 2 to get 1/8 is negative 3. The negative is required because that will give you the reciprocal of 2, but the reciprocal of 2 is only 1/2, and we want 1/8. So we raise that to the third power. So negative and 3, negative 3 will do the job. All right. And then finally, let's go ahead and take a look at one with a natural log. The natural log of e raised to the, let's do 2x, is equal to 12. So let's see, how do we do this? Well, we can first write natural log. We said earlier that the natural log is really just the log with a base of e, and the argument is e to the 2x equals 12. Now that we have the log written with its base clearly showing, the log base e, I can go ahead and write it in exponential form, where these two quantities here are going to kind of switch sides, and the e, this e here becomes big, and we get e to the 12th equals e to the 2x. And there's a property of exponentials that allows us to basically say if we have the same base e on both sides, we can just eliminate that base and set the exponents equal to each other. And you can see there, if you solve for x by dividing by 2, x is equal to 6. So the trick there is getting that natural log and rewriting it with as log base e. Again, you also might be able to maybe do that without rewriting it as log base e, but yeah, I'll just write it as log base e. Okay, so that's all I'll say there on number 4. Since again, we said we wanted to make this fairly short, there are some more complex problems coming up, so we will move on. Let's jump into problem number 7 for a moment. And let's see, did I leave? Oh, no, I didn't. One second here while I open up my problems from the textbook. Okay, so problem number 7. We want to solve a logarithmic equation. Let's go ahead and do something like the natural log. And let me switch colors here. This is problem number 7 now that we're talking about. And this is problem number 91 in our textbook. So the natural log of x plus 7 plus the natural log of 9 equals 2. Okay, so this is similar to part C in number 7. We'll just go over this one since it's the most complex one. And we can add these two logs together. Earlier we said there's a property for adding logs, and that was to multiply the arguments, right? So I will just apply that property that says I can combine these two logs, and I'm going to multiply the arguments. In this case, I can multiply the 9 by the x plus 7. And just to show the work, actually, I'll write it as 9 times x plus 7. If I multiply the 9 by the x plus 7, that means just to distribute the 9. And so we get the natural log of 9x plus 63. Now, I should have actually written my natural log as log with a base of e, because at this point now I want to get x by itself, but the x is inside of the argument. So how do I take it out of there? Well, I can rewrite this whole logarithm in exponential form using that equivalence relation that we gave earlier. E raised to the second power equals the 9x plus 63. And now we can solve this. I'm going to subtract 63 on both sides to get e squared minus 63. We can leave e squared just alone. If you have a calculator, feel free to approximate it if you like. And then divide both sides by 9. We're going to get e squared minus 63 divided by 9 equals x. So this is our answer. If you wanted to rewrite this a little bit, e squared minus 63 over 9, we could write it as 1/9 e squared minus 63 divided by 9 is 7. So, either one of these could be our answer. All right, very good. So that's problem number 7. We can combine any logs that we see, just as we did in this problem. And then once we have a single log equal to something on the other side, we can apply the equivalence relation that allows us to take a logarithmic equation and write it in exponential form. And that's what we did here. And then we can now solve that equation for x. All right, so a few different tools that we have to use there. Okay, now let's go ahead and go back to problem number 2. These are a little bit more complicated logarithmic equations, so that's why I wanted to do number 7 first. But it's really the same idea. Let's go ahead and take a look at something similar to problem 6C. And so I'll choose something from the textbook. Log base 4. Oh, actually, that one's in the textbook. Okay, let's do a different one. Log of x plus 8 plus log x. Sometimes there's no parentheses around the argument. If there's no parentheses, then it's just the x that we're taking. And then log of x plus 18. Here I need parentheses around the x and the 18 because I want both of them to be in the argument. Okay, so how do we solve this? Well, we see that there's a sum of two logs here. So we can just add the two logs together. If I add these two logs together, that's really multiplying the argument. So I'm going to just do that in one step. That's going to be log of x squared plus 8x equals log of x plus 18. Now I'm going to show another way to do this. If we have another log that's on the other side of the equal sign, we can subtract this log on both sides. And so we get 0 on the right-hand side. On the left-hand side, we have log of x squared plus 8x minus log of x plus 18 equals 0. So now we can combine these two logs because we know how to combine, we know how to subtract two logs. That is to divide the arguments. The base here is 10. So I'll write it in there because it's automatically 10 if there's no base displayed. And so now we have a single log equal to some number. We will go ahead and rewrite this in exponential form. That is going to be 10 to the 0 equals that whole mess. And so we can solve this by multiplying by x plus 18 on both sides. And 10 to the 0 is 1. So x plus 18 times 1 is x plus 18. X squared minus 8x. And then we can subtract x on both sides. Subtract 18 on both sides as well. Oh, hopefully this doesn't come out ugly because some of these do. And it looks like it is going to come out ugly. Okay, well, that's okay. We can just do it. But a lot of these on the worksheet will factor nicely if you get a quadratic. But it looks like, let's see, can we think of, oh, actually, this does factor nicely. Yes, we can think of two numbers that multiply to negative 18 and add up to negative 9, or can we? Hmm. Whoa, whoa, whoa. Did I make a mistake here? Ah, I'm just seeing that I made a little minus sign error. This should be a plus 8x, plus 8x, plus 8x. And so if I take 8x and subtract 1x, that's going to give me a positive 7x. Let's see, hopefully this will save us. Positive 7x minus 18. Can we think of two numbers that multiply to 18 and add up to positive 7? Yeah, how about positive 9 and a negative 2? Nice. So this factorization is x plus 9 times x minus 2 equals 0. And so x plus 9 equals 0, or x minus 2 equals 0. So x equals negative 9, or x equals 2. Now, remember that when you, so it seems like we have two solutions here, but remember that when you solve an equation, anytime you solved an equation in the past, what it meant for it to be a solution of your equation was that you could check your solution by plugging in the number, let's start with x equals 2, into the equation, and you can get a true statement. So log of 2 plus 8 plus log of 2 equals log of 2 plus 18. So if I punch this into a calculator, I should get both sides being equal. The left-hand side equals something and the right-hand side equals something. Well, and I don't even need a calculator here because, let's see, I get log base 2 of 10 plus log base, sorry, not log base 2, log base 10 of 10 and log of 2 equals log of 18 plus 2 is 20. And remember that the product, the rule that allows me to add these two logs would tell me that this is log of 10 times 2, or 20, equals log of 20. This is a true statement. There's no problem with the statement. So that means that x equals 2 is a solution. Yay. Now let's go ahead and check x equals 9. X equals negative 9. Well, let's start with log of -9 plus 8 plus log of -9 equals log of -9 plus 18. This is the original equation with just my x plugged into it, but you can see there's a problem right here. The log of -9 is not defined. Remember that earlier we talked about the domain of a logarithmic function. And we said that for the domain, the argument x plus 3 must be greater than 0. The argument needs to be greater than 0. Otherwise, that value, um, or we're outside of the domain of log. So if we take a close look at this, log of -9, this is undefined, which means this is not a true statement, and x equals -9 is what we call an extraneous solution. All right, and if I had a lot of time, I could talk more about, what this means, but essentially, this is a logarithmic function that looks something like this. Log of x is also a logarithmic function that looks something like that. Uh, the sum of these two functions is going to then we're trying to find out where it's equal to log of x plus 18, which is a logarithmic function itself. And so these two will intersect somewhere for some x value. And it looks like they intersect when x is equal to 2, because we got a true statement there, but only at x equals 2. Okay. Yeah, I don't want to rush that explanation there. So, we'll just leave it, come to my office hours if you want to talk about this some more. It's very interesting, but not really necessary for what we're doing here. Okay, so there we go. That's how you solve a logarithmic equation. Combine all the logs, rewrite that log equation. Once all the logs are combined, rewrite that equation in exponential form, and then solve that equation for x. Okay. I'll do one more example, or maybe talk about a shortcut way that we could have taken that would have saved us a little bit of time. But sometimes people use this shortcut in the wrong way, and so that makes me not want to show the shortcut. But I'll just show it because it is a good method. And basically, the shortcut comes down to this. Uh, Earlier, we said if we have two exponential expressions that are equal to each other, then we can just set the exponents equal to each other. If the bases are the same, we can just get rid of those bases. And so we got 2x equals 12. Well, there's a similar rule for logs. If we have two logs equal to each other, which I'll write them down again, here log of x squared plus 8x equals log of x plus 18. Then if we have two logs equal to each other, and those logs both have the same base, but it's just a log equal to a log and no other terms, then we can get rid of these logarithms and we just get x squared plus 8x equals x plus 18. And then we can solve from there. And if you take a look, that would essentially eliminate this step here, this step here, this step here, and we would start right here. Notice that's, equivalent to what we had there. So it eliminates a few steps, but the reason I just, fear here in sharing this is because sometimes students will use it the wrong way. This only applies when you have log base b of, let's say, ax plus b, some sort of expression inside of a log equals log base b of, 3x squared plus 10, or something like that. A log equal to a log and nothing else. Sometimes there may be a +7 here, like another term. And in that case, you can no longer just cancel out these log base b's because that 7 doesn't have a log base b with it. And even if it did, it just has to be a single log equal to a single log in order to be able to cancel out those logs. Okay, so if there was a +7 here, what you should do is subtract this log over to the other side, combine them using that subtraction rule of logs, and that's the method that I showed here. That will always work, whether there's, 2 logs, 3 logs, or, 5 terms. It doesn't matter. You can always combine the logs into a single log and then apply the equivalence relation to turn the logarithmic equation into an exponential equation. Okay, so an example of that where it comes up on the worksheet and students often make a mistake is in example 6b. Notice there's a log base 6 of x equals 1 minus log base 6 of x minus 5. You can't just cancel out those logs. In this case, you'd have to add the log base 6 of x minus 5 over to the other side, combine those logs, and then rewrite it in exponential form. All right. So that's everything there, or everything I want to say, or everything I feel I can say for a short-ish video. All right, and then we'll just quickly solve one of these equations for problem number 8. Let's see, 107 through 110, or the suggested problems in the textbook. So we'll do, so this is problem number 8 now that we're talking about, and we're going to talk about part B, something like part B, by solving problem number 109 in the textbook, which is 5 to the 2x plus 1 equals 9 to the x plus 1. All right. And I'd actually like to solve this first by solving the equation 5 times 2x plus 1 equals 9. And actually, I'm going to write this x plus 1 times 9. Yeah, just for fun here. Let's go ahead and solve this. Well, how would we solve this? We would solve this by distributing the 5 and getting 10x plus 5 equals, distribute 9, 9x plus 1. Then we would get all of the x terms on the left-hand side, 10x minus 9x, and all of the non-x terms we want to cancel out on the left-hand side and get them on the right-hand side, 1 minus 5. And of course, here we could combine like terms. I'm going to do this without combining like terms, and just stay with me here because this is going to be helpful for the next equation that we're going to solve. We won't be able to combine any like terms, and so the other way that we could solve this equation would be to factor out this x here. Both of these terms have an x, so I can take the x and factor it from 10x minus 9x, and we get 10 minus 9 equals 1 minus 5. And then whenever you have x times something, we're trying to get x by itself, so we can divide by 10 minus 9 on both sides. This might look a little weird because, you can say, well, you just combine those. 10 minus 9 is 1. But sure, 10 minus 9 is 1. And so I can divide by 10 minus 9 on both sides. So here is my answer. Of course, I could simplify this and we get -4 over 1 or -4. But that's not the point here. We're going to see that this exponential equation works out in a very similar fashion here. So let's go ahead and do that. And, we'll leave this beside it so we can kind of follow through and see the relationship between the two. So how do we solve an exponential equation like this. One way is to apply the natural log to both sides. And the reason that we want to apply the natural log is because we learned of a property that allows us, if we apply a logarithmic function, it lets us take the exponent and move it out to the front. And so if we move that exponent out to the front, we're going to get 2x plus 1 times the natural log of 5 equals x plus 1, which needs to be in parentheses, times the natural log of 9. And so notice that's why I wrote this 9 out here on the side, because now we need to distribute these logs, the natural log of 5 and the natural log of 9, into these parentheses. And so we end up with 2x times the natural log of 5 plus the 1 times the natural log of 5 equals x times the natural log of 9 plus 1 times the natural log of 9. Okay, and so you can see the relationship here between 2x times the natural log of 5. That's like this 10x. That's 2x times 5. Then there's a natural log of 5, which is just was played by the 5 earlier. X times the natural log of 9 is similar to x times 9, or 9x. And then finally, this number here is, similar to that number there. So how do we solve this? How do we solve this equation for x? We would get all the x terms on one side and all the non-x terms on the other side. So earlier we subtracted 9x. Well, here we're going to subtract x times the natural log of 9 on both sides. Get all the x terms on one side, and then all the non-x terms, like 5 earlier, we subtracted to put it on the right side. So here we're going to subtract the natural log of 5. Okay. And so we end up with, this is exactly why I didn't combine 10x minus 9x, because here 2x natural log of 5 will not combine with x times the natural log of 9, but that's okay. We don't have to combine it. Equals the natural log of 9 minus the natural log of 5. And so how do we solve this? Well, we said if they both have an x, just like earlier, they both had an x, we can factor out the x, and we get x, we get x times 2 times the natural log of 5 minus the natural log of 9 equals the natural log of 9 minus the natural log of 5. And so we have x times something. Well, let's go ahead and just divide by that something. We'll divide it, of course, on both sides. And then we have our answer. We can leave our answer in this form. It actually can be simplified a bit, but I think the answer in the solution for worksheet number 4 leaves it like this, so we'll just leave it like that as well. All right, so that is problem 8b. 8a is simpler than that, and 8c, it's very similar, but it has a couple of letters there, so yeah, we'll leave it at that. One of those is enough, to look at and think about. And you can see more examples in the textbook if you go into the sections of the textbook. Section 4.4, I believe, has a nice worked out example. It'll be very similar to the one I just did. All right, finally, we've finished problem number 8. We'll go through number 9 and 10 here very quickly, and then we'll call it a day. For problem number 9 and 10, I'm actually going to go to the actual worksheet, and I'm going to just make up a couple of problems. I won't do the ones on here to give you a little bit of, to allow you to do those, but I will do similar problems. So y equals 2 to the x, I will do that one because that's just the parent function, and it's very important that we know that one. Okay, so let's see. It would be good to have the numbers. So we're just going to take some x values and plug them in. And the y value, the output is going to be 2 to the x value. So we'll start with 3, 2, 1, 0, -1, -2, and -3. Starting at the top, 2 to the third, well, that's 8. 2 to the second, that is 4. 2 to the first is 2. 2 to the 0 is 1. 2 to the -1 is 1/2. 2 to the -2 is 1/4. And 2 to the -3 is 1/8. Okay, so we can plot these. 0, 1 is right there. 1, 2 is there. 2, 4 is there. 3, 8 is way up here. -1, 1/2 is there. -2, 1/4. -3, 1/8. And so we can see the behavior of this function. It rises very quickly up to positive infinity, but then it has a horizontal asymptote here at y equals 0. So I'll mark that in red. So if we know this parent function really well, we can graph any transformation of this function. So I'm going to graph y equals 2 to the x minus 2, and then we'll do minus 5. Let's do that. And basically, if you want to graph this super quickly, what you need to know is you need to know the parent function. Here, I'm going to graph it again. This. And then we're just going to move each point 2 units to the right. And then that -5 is 5 units down. So let's start with this point here and go 2 units to the right. 1, 2, 1, 2, 3, 4, 5. There we go. And if we do this to every point, 1, 2, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5, 1, 2, 1, 2, 5. 1, 2, 1, 2, 3, 4, 5. Zoom in a little bit. Here's the next one. Here's the next one. And we would look something like this. Very good. There is our graph. Our new asymptote is going to be at y equals -5. Even the asymptote goes from y equals 0 down 5 units to y equals -5. So let's talk about the domain and range here very quickly for y equals 2 to the x. The domain is all real numbers. That's the domain of basically any exponential function. The range, you can see from the picture, is going to be 0 to infinity. It doesn't actually hit the value 0. There's a horizontal asymptote there, but it does go up to positive infinity. And so if we realize that it is shifted to the right 2 units, the domain will just stay the same. But the range, since it's shifted down 5 units, it will go down to -5, or it'll approach -5 and then go up to positive infinity. Okay, so we could also even apply these transformations of 2 to the right and 5 down to our table. 5 down means I subtract 5 from the y value. So this is y direction. So if I subtract 5 from each of the y coordinates in this column here, I'm going to do that really quickly. 8 minus 5, 4 minus 5, 2 minus 5, 1 minus 5, a half minus 5, 1/4 minus 5, fourth, that would be -4 3/4, so 4.75. And then an eighth minus 5 is, an eighth is 0.125. And if we subtract 5 from that, that will be -4.875. Yeah. Okay. And you can see that, and then 2 to the right, that will be x direction. And so if we move to the right, that means we increase all the x values by 2. So let me increase them by 2. 3 plus 2 is 5. 2 plus 2, 1 plus 2. Okay, there they go. And so notice I just adjusted my parent function table. And if I plot these points now, these are exactly 5, 3, which is this one here. 4, -1, 3, -3, and so on. 2, -4. Oops. 2, -4 is this one here. 1, -4.5, and so on. Okay, so you can either do it by shifting the points, or you can draw the table of the parent function and then just apply the transformations to that table. And there you go. Okay, so knowing the parent function really well is going to do you some good. And then knowing transformations is going to help you out as well. So if you forgot some transformation stuff, you want to go back and review it. So let's do one more problem here very quickly, and then we'll do the logs, and then we'll end the video. Okay, so we'll do something very similar here. Y equals, and I'm gonna do, yeah, let's do uh, negative 2 to the x, and we'll do plus 3. Okay, so what this is going to do is reflect about the x-axis and then up 3 units. Okay, so if I know what my 2 to the x looks like, I'll just graph it here in, let's do blue. There and 2, 8. Oops. Okay, so here's my parent function. I just graph the dots. If I reflect it about the x-axis, it's going to look like that. And then if I shift all these points up 3 units, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And there's my graph. Notice how quickly I did that. If you know the parent function well, and you know function transformations, boom. Takes just a matter of seconds. No calculations were needed really there. And I've got the whole graph, very accurately graphed. If you want to avoid learning function transformations, which I would strongly recommend against, but hopefully you already learned it. But the other way would be to, okay, just plug in a bunch of x values like -3, -2, -1, 0, 1, 2, and 3. But now you're going to have to, plug all of these in, find the y values. You'll end up getting exactly the same points that I plotted, but it just takes a whole bunch of calculations. All right, so the last topic for today is the log function. Okay, so I don't want to spend too much time on this because this video is already long, but just a little bit of time. 1, 2, 3, 4, 5, 6. So it turns out that the log function and the exponential function are inverses of each other. So one way to actually do this, to graph this parent log function, the log base 2 of x, is to just take the x and y values from the 2 to the x function and just switch the x's and y's. Because they're inverse functions, we know that the x's and y's just switch, and then we can graph that. That's essentially what we're going to do, but actually I want to just do a couple of them first by hand, the long way, and then show, well, this is just the table that we had before, but flipped. Okay, so let's go back to log base 2 of the input here is 8. So the question that's being asked here is, what exponent do I need to put on 2 to get 8? And we know that that's 3. What exponent do we put on 2 to get 4? Well, that's 2. What exponent do we put on 2 to get 2? Well, 2 is already 2, so just an exponent of 1 would do. What exponent do we put on 2 to get 1? Well, we know 2 to the 0 is 1, so the answer there is 0. And we just continue in this way. What exponent do we put on 2 to get its reciprocal? Well, a negative 1 of an exponent will give us the reciprocal. And if you ever forget one of these or how to do these, remember that you can just say, well, this is equal to y, and we can use the equivalence to write this as 2 to the y equals 1/4. And so again, we're asking the question there, what exponent do we put on 2 to get 1/4? And hopefully you remember that that's negative 2, and the last one is negative 3. So if you take a close look at that table, that's just this table with the columns switched. X and Y are switched. Okay, so we can graph, let's see, 8, 3, 4, 2, 2, 1, 1, 0, 1/2, negative 1, 1/4, negative 2, and 1/8. So this function looks like this. It's going to have a vertical asymptote. And notice, this is pretty cool here. It's kind of going with what we said earlier. What's the domain? Remember that we said the domain was that the argument, x, needs to be larger than 0. And we can see, well, that's actually the domain of this function here. The domain is that all numbers from 0 to infinity, not including 0, because we have x is strictly greater than 0. The range, well, the range is just going to be the domain of the inverse function. So it's going to be this here. And we can tell from the picture here, it looks like it goes down to negative infinity. And then this log function does increase forever to positive infinity. It increases fairly slowly, but does continue to increase. So some of the stuff that we've gone over before is kind of coming together here. And the last problem that we'll do here is something similar to d log base 2 of, yeah, we'll just do negative x plus 3. Okay. And I'm going to start by doing, I'm going to do it with a table by adjusting the table of the one that I already have in blue, the blue table. Oops, that's not what I want. Rectangle. 1, 2, 3, 4, 5, and 6. Okay. All right. And so what I'm going to do is, let's see, this plus 3 means add 3 to the y values. And the negative inside of the function, this is reflect about the x-axis, sorry, about the y-axis. And that means that I multiply the x values by -1. So all of the x values are going to become negative, -1/8, -1/4, -1/2, -1, -2, -4, and -8. And then all of the y values are going to increase by 3. So I'm going to get 0, 1, 2, 3, 4, 5, and 6. So let's plot these points and see what we get. I'm going to start with -8, 6, -8, 6, there, -4. And before I do that, actually, um, everything is shifting up 3 units, so the range is going to be increased by 3. Well, okay, negative infinity plus 3 and infinity plus 3 are still the same. But then the y, oh sorry, the x's are reflected. So what's the domain going to be? Well, we can again use what we learned earlier, that the domain of oops, I'm looking at the wrong function here, but this one right here. The domain of a logarithmic function can be found by just getting the argument and setting it greater than 0. If we divide by a -1, we're dividing an inequality by a negative, which means we flip. And now it's x is less than 0, which is negative infinity to 0, which makes sense. It should now be negative or to the left of 0 because we reflected about the y-axis. Right? So let's go back to graphing. There should be a vertical asymptote now at 0 because the domain ends here at y equals 0. But -8, 6, -4, 5, -2, 4, -1, 3, -1/2, 2, -4, 1, and -1/8, 0. Our function looks something like this. Notice, I mean, and that one I did do some calculations because I used the table, but if I had just taken every single point and reflected it about the y-axis, you know, and then shifted these all up 3 units, we'd get exactly the same graph. So I don't really need to do much calculation if I don't want to use that table method. I just wanted to show you that you could do it with a table. There is another way to do it as well, and that would be just to plug in x values. But the plugging in of x values is a little bit tougher just because you have to know what x values to plug in. I can't just choose, like, let me plug in a 7 or something like that. Because first of all, well, a -7, you can't take the log of. But if I plug in a -7, well, now I do get a positive number in the argument, but I don't know what the log of 7 is, right? So then I have to be a little bit more choosy with my inputs, and I plug in, okay, well, let me plug in -8. Oops, and this is log base 2. Well, this will work here because log base 2 of these negatives cancel of 8. What exponent do I put on 2 to get 8? That's 3. And if I add 3 to that, I get 6. So notice if I plug in -8, my output is 6. Well, that's exactly what this point here is saying. So I recommend knowing the parent function really well, memorizing this basically, and really to memorize this, the log function, the log parent function, it's really just the exponential parent function reflected, or with x and y switched. So if you know this one well, this one you just switch an x and y for and graph, and then you can just use function transformations to graph any of these in a matter of seconds. All right. Yeah, well, sorry I went long here. There's 2 videos since my pen died in the middle of one. But hopefully that was a pretty good review of that kind of stuff there. There is one more problem there. I'll talk about it in class. It's not too complicated. It's not that bad. All right. So we'll end the video there. Maybe leave a like on the video and put a comment or something. Say, tell me if you like the video or not, or if you want me to keep making videos, let me know and I can try to tailor them to to the content that we're going over in each worksheet. I do have another video that I made a year or so ago. Feel free to watch that one. It's, it goes in depth into the material that we're covering here in this worksheet. All right, so yeah, let's go ahead and end the video before my pencil dies again. See you in the next video.